I want to start today's lecture by recapping the last few concepts that were discussed in the last few lectures. So one of the concepts is a Newtonian fluid. So the concepts related to this are shear stress, dynamic viscosity, and strain rate or velocity gradient. So for Newtonian fluid, dynamic viscosity is constant and it is defined as the relationship between shear stress and the strain rate or velocity gradient. So if shear stress tau is equals to dynamic viscosity times, that is mu is the dynamic viscosity, times gamma dot is the strain rate, which is equals to mu times du dy, where u is the velocity and y is the distance from the surface. So this is also called the velocity gradient. To understand the velocity gradient, let's consider a solid surface. It's a solid surface that doesn't move and it's plane. So you're looking at this in cross section. So for example, if this is the surface, and then above the surface there's some liquid flowing over it. There's a stream of liquid flowing over it. So let's draw it a little bit more diagrammatically. So that's the solid surface, and there is liquid flowing at a full rate over here. Now, recapping from the previous lecture, what we said is that the velocity of the liquid flowing near the surface is 0. So very close to the surface, according to the no-slip boundary condition, the velocity of the liquid is almost 0. As you go further away from the surface, the liquid flows faster and faster. So it could be a liquid or a gas. So we call it a fluid. So the fluid flows faster and faster as you go away from the surface. So if you plot the velocity with respect to the distance from the surface, so the distance from the surface is called the transverse coordinate. So let's draw it over here like this. So that's the transverse coordinate y, and the velocity u. So this is u0 is the velocity at the surface. So u1 is the velocity at distance 1 from the surface. So this could be 1 meter, 1 centimeter, so in some distance units. And u2 would be velocity at 2 units from the surface. So we said, so let's say this is velocity 0, and let's say there is a velocity, maximum velocity away from the surface. Let's call it UMass. Then, so at y equals to 0, u equals to 0, so we have 1 point here. Let's say at y equals to 1, use some value, y equals to 2, use another value, and if you draw this, this becomes something like this, where as you increase your distance from the surface, so the transverse distance, the velocity increases until it reaches the maximum velocity. At large distances from the surface. So if you look at each point, this has a slope. So let's say around here, there's a slope, and that slope would be du dy. So if you look at here, this would be 1 du dy at u equals to 0 or y equals to 0. So this would be du dy at y equals to 1, let's say y equals to 1. So there would be different slopes at different distances from the surface. But if you plotted the shear stress with respect to the velocity gradient du dy, so this is also called the rate of strain or the strain rate. So it could be mu times strain rate. Then if mu is constant, then this is called a Newtonian fluid. Newtonian implies mu or dynamic viscosity is constant. So let's look at this graph. In one axis, the horizontal axis, we have the velocity, and the velocity, as always, is measured in meters per second. And in the vertical axis, we have the transverse distance or the distance from the surface, and it's measured in meters. Now, if you look at this curve, if you look at 1 meters per second, then you are at, let's say, half a meter. And if you're at 2 meters per second, let's say you're at 1 meters. Then the slope of this segment, du dy, so let's say du dy at this location between 1 and 2, or at 1 or at 1 at u equals to 2, is equals to the change in u, which is 1, divided by the change in y, which is 0.5, which is equals to 2, and the units are meter per second divided by meter, so it's per second. Now let's look at another segment, for example here. If we look at the segment here and here, so around here, if we consider that this is a approximately straight line from here to here, then the change in u is just 0.5 du dy is equals to 0.5, which is 4.5 minus 4, so it's 0.5 divided by the change in y is about, let's say, 2.25 to 3.25, so about 1, which is equals to 0.5 per second. If you remember, the strain rate or the slope of this curve when u with respect to y was 2 per second. So if this is a Newtonian fluid with a given dynamic viscosity, for example, if the dynamic viscosity is equals to 1, then the shear stress, which is measured in pascals, is equals to mu times du dy, which is equal to, over here this is equals to 2 pascals, while over here it's equals to, near here, tau is equals to 0.5 pascals. So you can see that as you move away from the surface, the shear stress decreases. So high shear stress here and low shear stress here. So the shear stress right at the surface can be is where the solid and the liquid interacts. So right next to the surface, so let's say this is the solid surface and the fluid is flowing over here very slowly. Far away it's flowing faster, but the shear stress is lower. Near the surface is high shear stress, or um, rate of change of the velocity is greater near the surface. So if you consider a blood vessel, let's say this is a blood vessel, it has a wall, and this is the space, internal space of the blood vessel. So you can imagine it's like a pipe. So this internal space is called the lumen. So this is the lumen. So the cells that are immediately next to the lumen, so there's some cells lining the lumen, they're called the endothelial cells. So these are the endothelial cells. So if you imagine that I zoom into this portion of the tube or the blood vessel, then I can draw the endothelial cells. Let me erase this. So I can draw the endothelial cells like this. And the blood is flowing slowly on top. So the blood is flowing like this into the blood vessel inside. And if you zoom into this portion, then near the endothelial cells the blood is flowing slowly, but as soon as you go a little bit further it's flowing faster and faster. So you have a lot of shear stress, and near the middle of the tube the blood is flowing at its full speed. So right here there is a lot of shear stress, and because the shear stress applies to the solid, it will try to pull on the solid. This shear stress at the boundary, if you're talking about endothelial cells, is called the endothelial, not surprisingly, the endothelial shear stress, or ESS. So why do I mention this? It is because many people have studied, or a lot of biomechanics or cellular biomechanics these days is dependent on the theory that a certain range of endothelial shear stress creates a certain biological effect. For example, in the blood vessels of the heart, if the endothelial shear stress is too low or too high, it might create an inflammation, eventually leading to a heart attack. Or in the brain, if the endothelial shear stress in the blood vessels are of certain range, then one theory that is prevalent right now is that it might create aneurysms, or the aneurysms that are already there might rupture.